Hi guys, this video is about Taylor series, and it sort of continues from the previous lecture that I gave to you about power series. So if you haven't watched that one yet, I recommend that you do that first and then you can come back to this video later. Alright, so back to Taylor series. What is Taylor series? We are going to start with that. So the first thing you should know about Taylor series is it's a special type of power series. So here, Taylor series, a special type of power series. What this means is that Taylor series would be subset of power series and must have the same properties as the power series. So let's talk about those properties here. Number one, just like the power series, Taylor series must have a variable in the series. Have a variable. And let's use x for that. The next thing that Taylor series must have is this property. Number two, just like power series, it must be built at a certain location or a point. Built at a point. Let's use A for that point, just like what we did in the power series. And number three, last one, Taylor series would have the same formula as the power series. So let's bring that formula here. Power series is infinite, so we have the sum sign, start at n equal to 0 and ends at infinity. Well, I should say that it never ends. It keeps going, all right? And the next term is the constant term with the index n. It means that each constant can be different for each term. Now, the next one is the polynomial term, x minus a to the power of n. This is the formula for the power series, and Taylor series would have this form as well. All right, so the next thing we should know about Taylor series is its usage. What is it for? Why do we need to learn about it? All right, so here's why. So Taylor series can give us the approximation of any differentiable function. All right, so this is the key. Taylor series can give us the approximation of functions, but those functions have to be differentiable, and we use the notation C1 for that. All right, C1 here means differentiable. And C0 means continuous. All right, so approximation is the main usage for the Taylor series. And due to the form of this series, which have the polynomial term x minus a, we usually call this polynomial approximation of a function. Okay, so we know what it is, we know what it is for. Let's try to make this happen. Let's try to perform the approximation. So about how it's going to happen, so let's take a look here. If you have any C1 function out there, any C1 function, and you want to find the approximation of that, you can transform this C1 function into Taylor series. Okay? The question is, why do we need to do this? Why do we need to transform a function into an infinite series? The reason, the answer for that is because sometimes the function it can be complex or complicated, and it can be hard to compute. Once you transform this function into a Taylor series only have polynomial terms, and they are quite easy to manage with the computations. So that is why. All right, so this approximation are supposed to be easier to compute. All right, easier to compute and process. Okay, now let's take a look at this transformation. How do we go from a C1 function to Taylor series? So let's take a look at the next line. So we have this C1 function fx here, And what you see on the right hand side, that is an infinite series, and this one is Taylor series. What you see right here is Taylor series. At the first glance, it might look quite messy and complicated, so let's take a look further into this series term by term so that we know about the details of each term. So let's take a look at the first term. We have this function value evaluated at a. Then we have this first derivative of f evaluated at a again. And then we have this polynomial term with the power of 1. Okay? Now the next term we have second derivative evaluated at a and divided by 2 fact. And then we have this polynomial term with the power of 2. Okay? Next we have this third derivative evaluated at a divided by 3 fact. And then we have this polynomial term with the power of 3, and it keeps going and never ends to infinity. At this point, I think you should be able to notice the pattern of each term of this. So let's find the compact form for this infinite series to save some space. Alright, so here is the compact form. We are looking at an infinite series, so definitely we would have this sum sign. And the index for each term is going to start with 0 and never ends, goes to infinity. Now let's find the next one for this compact form. As you can see here, for each term that we look at the series above, we see this function, also function, and function, and function. So definitely we have this function evaluated at a. But it's not just that, because each one of them has different orders of derivative. So definitely we have this f evaluated at a, but not just f. We have this order of derivative, and it starts at 0. 0 derivative of f is basically the function itself. Then we have this first order, second order, third order, and it keeps going. So what we have here is this index k. Indicates the order of derivative for this f. Alright, now we have something more, but before we talk about that, let me add this divided by 0 fact, 1 fact here, which changed nothing because 0 fact is equal to 1, and same for the 1 fact. So as you can see here, the 0 term has this 0 fact. First term has 1 fact. Second terms have 2 fact, 3 fact. And of course, right here we have this k factorial. Alright. Now, let's take a look at the next one. We are looking at this polynomial term. Alright, so let's put it here. X minus a. And as you can see here, with the 0 term, we don't have x minus a. So this power would correspond to k right here. K equal to 0, this is gone. K equal to 1, we have first order, just like the series we see above this. Alright, so what we have here is the compact form of Taylor series. Let's make a box around that. Alright, so this is Taylor series. Now let's do something. What about I circle this and make this equal to ck? When you do this, you can see that it's the same as this formula, and that is why Taylor series is also a power series. But the only thing that's different from the ones we have seen so far is the details inside this Cn, which is this, well, different order of derivative of f divided by k fact. Okay? Alright, let's move to the next slide. So here we have this compact form again, the formula for Taylor series. Everything is written here, and let's take a look at this infinity sign. I told you before that we do the approximation by the Taylor series to make the calculation better, easier, right? But how is that going to be easier if we have these infinity terms to compute, right? Well, the polynomial term might look simple, but with the amount of terms we have here, not going to be easy. So this means that in practice we only use 2 or 3 terms of this to approximate. So this is the key. We usually only use 2 or 3 terms, right, for the approximation of the fx. So with the infinite terms, fx would be equal to the whole series. But if you take only 2 or 3 right here and equal to 2 or 3, what we have here is just the approximation. All right. If you want to make it equal, take all the infinite terms. If you make the approximation, just take some of them and make the calculation more manageable. All right. So n right here is finite. You can pick 5, you can pick 10, but it's going to be better to pick smaller numbers. Okay, now when it comes to approximation, we need to know about one notation. We sometimes use P1, P2, P3 to indicate the approximation of function by Taylor series. So let's take a look here. P1, P2, and P3. At first glance, you might think that P1 must have maybe 1 term, but it turns out that P1 we need 2 terms of Taylor series. P2, 3 terms, and P3, 4 terms. Why is that? The reason for this is because P1 represents the first order polynomial approximation. First order polynomial approximation would have this k equal to 1 right here. This is the same 1 right here, same as this 1. But our series start at 0, which means that we need the 0 term and the first term, all right, which would give us the first order polynomial approximation, 2 terms. And for P2, we need 3 terms because we start at the 0 term first and then second order polynomial approximation. Next one, P3, we need 0, first, 2, and third, and in the end we would have this third order polynomial approximation. All right, so you need to know about this notation because we need that for the examples down here. We have 3 examples, but let's do just 2 to save some time. Let's do number 2 and number 3. So what is it asking us to do? They ask us to find P3 approximation. So obviously we have to do this 4 terms. All right, so let's start with the square root of x. In this example, we have function of x equal to square root of x, and we want to find the P3 approximation of this function by using the Taylor series. So the first thing I'm going to do here is to check if this function is differentiable. But when I see this square root of x, I know right away that I can differentiate this. So it means that this is differentiable, this function. And that is good because it means that we can use the Taylor series to find the approximation of this function. Now, the next thing we are going to do here is to bring the P3 approximation formula to this example. So P3 approximation right here. And P3 stands for the third order polynomial approximation, and as we know, we need 4 terms of the Taylor series to complete this formula. So let's put them here. P3 equal to, first term is the function value evaluated at a. Second term is the first derivative of f evaluated at a. And polynomial term x minus a. Next term, second derivative of f evaluated at a, divided by 2 fact. And once again, we have this polynomial term, x minus a, but this time is second order. Last term, third derivative of f evaluated at a divided by 3 fact. And polynomial term, this time, has the power of 3. So as you can see here, we have this power of 3, definitely third order polynomial. So the next thing we are going to do here is to fill some numbers into this formula. And we can see that in this example, we need to build this Taylor series at a certain location, and that location is a equal to 4. So let's put this number into this formula. And as you can see here, we have a right here. Let's change all of these to 4. So this becomes 4, 4, 4 here, 4 here, and that's it. Oh, one is missing right here. So this formula looks better now, but it's not done yet. So we still have some computations to do, and as you can see here, we need to compute 4 values of function and derivatives. Function, first derivative, second derivative, and third derivative, all evaluated at 4. So let's find them. Let's start with the first one, that is fx, and that is equal to square root of x. If we differentiate this one time, we get the f prime of x equal to 1 over 2 square root of x. And since we need the second derivative, let's differentiate this again. So we get this f double prime of x equal to minus 1 over 4 x to the power of 3 over 2. And last one, the third derivative, f triple prime of x is going to be equal to, let's diff this again, we get 3 right here, and then we get 8 down here, x to the power of 5 over 2. And we want to know these terms when x or a equal to 4. So let's find them. When x is equal to 4. So here we have this f at 4 would be equal to 2. Alright, let's just put 4 in. Now f prime at 4 would be equal to 1 over 4. Now f double prime at 4, and this would be equal to minus 1 over 32. Alright, and then last one, f triple prime at 4 would be equal to 3 over 256. Alright, so we have all these numbers, and the only thing that we need to do right now is to put them in to the formulas that we have. So P3 up there would be here again, and the first term is f4, and that would be 2. Next, f prime at 4, that's 1 over 4, x minus 4. Next, we have this f double prime, and that would be minus 1 over 32. And we also have this 2 fact right here. Okay, let me fix this. I want this to be to look better right here. And we have this polynomial term, x minus 4 power of 2. Last term, we have f triple prime, and that is 3 over 256. But then we have 3 fact right here. Okay, and x minus 4 power of 3. So let's work out these numbers. Do not leave it like this. Okay, so this P3 is going to be equal to 2 plus 1 over 4. You do not need to multiply this 1 over 4 in. Just leave it like this. Let's keep the pattern of the Taylor series intact. But for these numbers right here, you can work it out. Minus 1 over 64. And this x minus 4 square to square. Last one, 1 plus this 3 cancel with that, and we have 2 fact here. So in the end, we have this 1 over 512 x minus 4 to the power of 3. You do not need to work out this square or the power of 3. Leave it like this. This is enough for the final answer. The reason for that is because we want to keep the pattern of the Taylor series to be there. Alright, so here is the answer for this problem. P3 approximation of the square root of x. Alright, this is approximation, well, let's put P3 here, of square root of x. So if you want to compute square root of x, but you don't want to use square root of x directly, you can use this instead. Alright. Okay, so let's do one more example, and that would be this one. Okay, so we have this function of x again. It's polynomial, quite long, and then we want to find the P3 approximation of this. Of course, the first thing we are going to do here is to check if fx is differentiable. And you can see all these terms. And definitely we can differentiate this. So everything is good. Let's use the P3 formula here. So P3 formula, once again, just like the previous example, would be f at a. And we have a equal to 1 here. So that would be f1. Second term would be the first derivative of f evaluated at a and a equal to 1. X minus a equal to 1. Alright. Next, second derivative at a. That's 1, and x minus 1 to the power of 2. Last term, oh, I forgot the 2 fact right here. And the last term would be third derivative of f at 1, alright, divided by 3 fact. And we have this x minus 1 to the power of 3. Okay, and as you know, all we need to do is to find this value, this one, and this one, and it's mostly done, alright? So let's find them. Fx would be equal to 2x cubed, right from the problem, plus x squared plus 3x minus 8. And if I compute this, I can find this f1 to be equal to, let me check, that would be equal to minus 2. Alright, so let's check again. 2 plus 1, 3, 6 minus 8, okay, minus 2, that's correct. So let's differentiate this one time to get the f prime of x, and that would be 6x squared plus 2x plus 3. Alright, and we want to find this first derivative at x equal to 1. Let's put 1 in, and you can see that we get 11 out of that. Alright, next one, second derivative. And we diff again, we get 12x plus 2, and put 1 in. We can evaluate this at 1, and it's going to come out to be 14. And the last term, third derivative, diff again, we get 12, and obviously this one is equal to 12 at x equal to 1. That would be equal to 12. So we need to do here, what we need to do here is just to put these numbers in to the formula. So we have this P3 equal to minus 2, the first term, okay, plus first derivative, that is 11, x minus 1, plus second derivative divided by 2 fact. So here would be 14 divided by 2, so we get 7 right here. Okay, and x minus 1 square. Next term would be this one, the third derivative divided by 3 fact, or 6, and we have this 12, so 12 divided by 6 would be 2. X minus 1 to the power of 3. Okay, so you can use this as the final answer because we work out all the numbers already and we keep the pattern of the Taylor series just like it's supposed to be. Okay, so what we see right here is the P3 approximation of 2x cubed plus x squared plus 3x minus 8. And that is it for this example. And as you can see here, if you know what to do, it doesn't take long at all to complete this P3 approximation.